In this lecture, we introduce the basic pieces of HDF5 and describe how they can be used to solve data management problems. In the modern world, analysis problems can be very complicated, with lots of pieces that interact. The result is large quantities of data that piles up in different formats and in different locations. Dealing with this large variety of file formats and locations takes up valuable time. For example, the need to write parsers or scripts that read information from different file formats is time not spent on analysis. Also, it's very easy to separate the data from the context information or metadata that's required to provide a consistent picture. Importantly, this is not only a problem with the sheer quantity of data involved, it's also a problem for sharing data. So what we need is a technology that can cope with large amounts of data of different kinds, while still providing fast, efficient access to that data, bundling metadata or context information that makes the data useful, and also allows us to easily share all of this information both across people and across platforms. HDF5 helps you solve this problem. HDF5 files provide data objects that can store numerical data, a way of handling metadata, which means you can provide context information, and also a mechanism to provide structure to indicate that different pieces of data have some relationship. In the HDF5 universe, this problem is addressed in an extraordinarily simple way. HDF5 provides only 3 data structures, which are enough to solve this entire problem. The first, datasets, are the equivalent of NumPy-style ND arrays that can be stored on disk. The next, attributes, are a mechanism for storing metadata in key value form directly attached to the objects it describes. And finally, in a way similar to folders in a file system, groups allow you to bundle objects together and indicate that they're logically related. These 3 basic building blocks allow you to construct solutions to complicated domain-specific problems. To start with, datasets are the mechanism in HDF5 for storing large quantities of numerical data. You can think of them as NumPy arrays that live on disk. Just like NumPy arrays, datasets have a well-defined shape and type, and they can be sliced. In other words, they support partial access, and you can read only the portion of that data that you want. This is very important because in HDF5, there's no practical limit on how large a dataset can be. It's very easy to create and manage multi-terabyte datasets in HDF5. And because HDF5 is platform independent, the files that you create can easily be shared not only between computers, but also between environments. The next piece of HDF5 is attributes. Attributes allow you to attach key value metadata to any object in the file. Importantly, this means that metadata, or context information, is always located right next to the data it describes. So, when you share your information with other people, they can very easily understand what it means. All the information required to make sense of your data is stored right there in the file. This is a big part of what makes the HDF5 a so-called self-describing format. In other words, you can interpret the meaning of the data without having to reference other documents. For example, you might have an array or a dataset in HDF5 that contains image information. This would be communicated by a series of attributes that describe properties of the image. The final HDF5 building block is groups. Groups are an extremely powerful way to organize objects in your file and provide structure. Much like folders in your file system, HDF5 groups are used to represent logical relationships between objects that have different shapes or types. And because groups can be discovered and browsed, much like folders, they're a big piece of making your HDF5 data self-describing. What does it mean to be self-describing? In the HDF5 world, it means that you can skip the step where you write a long parsing script to pull data out of a file. In Python, this means you can interact with groups, attributes, and datasets in a very Pythonic way. In other words, groups and attributes use the dictionary metaphor that can be iterated over. They have keys and values. And datasets behave like NumPy arrays. You can slice them, and you can examine attributes like shape and dtype. It also means that files you write from Python can also be explored in other environments that support HDF5, like MATLAB. And this extends to any HDF5-aware tool. For example, the graphical viewer program HDFView can understand any file that you write, because both of them use HDF5. HDF5 comes with many other features that can help to solve problems. For example, Much like the NumPy structured array, you can define compound types in HDF5 that represent table-oriented problems. HDF5 datasets, created with the right options, can also become dynamically resizable. So, for certain problems, where you may not know ahead of time what shape you want, HDF5 can adapt. HDF5 datasets can also provide transparent compression, which means that you can read and write data as normal, but HDF5 will compress that data when stored to disk. And HDF5 comes with a variety of different storage methods that allow you to optimize access for different use cases. Let's talk about how people use these HDF5 building blocks to solve problems in the real world. In the HDF5 world, conventions are a standardized arrangement of groups, datasets, and attributes that are used to solve a domain-specific problem. Here's an example. BAG is used by the ocean science and navigation communities to describe ocean water depths. So, a BAG file holds 2D datasets that represent the depth and uncertainty of the depth over a particular area of the sea. In addition to that data, attributes are used to hold information summarizing the full range of values. And other datasets in the file hold information about who created the file and how it can be used. Another example is the MINC format. Like BAG, the MINC format is a series of conventions on top of HDF5. It's used to represent medical imaging data. In MINC, groups are used extensively to bundle datasets that represent an image. Likewise, information on location required to make sense of the image is stored as a series of datasets under a dimensions group. And attributes attached to both the groups and the datasets provide essential information on the orientation of the image, how it was acquired, and other details. So, to summarize, HDF5 is based on just 3 simple elements: datasets that store numerical data, groups that provide organization and structure for that data, and attributes that provide the context information required to make sense of it. Datasets can handle very large amounts of data and can be of many different types. HDF5 provides fast, effective partial I/O that allows us to read and write only portions of the data that we care about. Attributes allow you to store context information or metadata in the file right next to the data that it describes. Groups provide the organizational glue that holds it together. Together with attributes, good use of groups make your HDF5 data shareable, discoverable, and self-describing. And finally, communities, which can range from a small lab to a large standards organization, can agree on conventions on how to use groups, datasets, and attributes to represent a problem.